Hello and welcome back to Calculus 1 section 3.6 on derivatives as rate of change or rates of change. We know how to take basic derivatives because we learned the shortcuts. We know the painful way to take the derivative, which was the that limit of the difference quotient. And now is time to put that in perspective through some application, even though the next chapter is application only. So, first off, when someone says rate, you immediately think A over B or f of x over g of x or dy dx. These are all rates. They're all divisions, right? So now to understand the rate, and the one that we will use a lot, you can think about the rate of change as you're driving. You are looking at the speed and it's in miles per hour. So you can think of the rate miles per hour. Now, miles is distance and the hour is time, and you get the speed at which you are driving. Now, in this lesson, we are going to distinguish between the average rate and instantaneous rate. Average rate would be the one that you learned long time ago, which is just the slope of the line or the average, right? And the instantaneous rate would be the derivative. So that's what we are going to make clear today. Now, when you're talking about miles per hour, if you say you're driving 60 miles per hour, this means we go 60 miles in 1 hour. So we cover 1 mile a minute. This particular statistic is really cool because you can use it as you are driving. You can average the highway 22 and highway 78. One is speed limit 55, the other one is speed limit 65. If you average them, then they're both 60, right? You always have people in a left lane driving 20, right? So there are no guarantees that you will be driving over the speed limit as you go somewhere, but you know, on 55 you drive 60, over there 65 you drive 60, so just call it 60, okay? When you're driving 60, and let's say you are on a big highway that has exits, United States did a pretty good job in trying to organize itself so that there is some kind of order for the roads, and I'm not sure if you know this info or not, but all of the roads that are going north-south should have odd numbers, like 287. And then all of those that go east-west, like 78 and 80, should be even. Doesn't hold for 100% of the roads, but most of them have followed that rule. And then you also have the mile markers, which show how far you are from the point of entry in the state of New Jersey, let's say. And your highway 78 goes through Pennsylvania, right? But at the border between Pennsylvania and New Jersey, there is a mile marker 0 for 78, which is the New Jersey part of 78. So now you have exits. Yeah, and you would have, let's say, exits 15 and 17 for Clinton. You will have exit 18 for Annandale. These exits follow mile marker, which means that if you see exit, let's say, 29 over here, or 26 for our college, that means you are 26 miles away from where the road started. If you have to drive through the entire state, and you are on a highway and you are starting with the exit 138, that means you have 138 miles until you are done with that state. So each mile there is an exit, and if there is no need for exit, they will skip it. So you know that there is exit 18, there is exit 20, there is exit 24, there is exit 26, and then there is exit 29, right? There is no exit 27 because there is no need for it. So exits follow the miles, and you can always approximate, if you use this about a mile a minute, you can approximate how far you have to go and so on. I used to use that a lot, those approximations, when I used to commute. You know, you just need to be driving around 60 miles per hour and it would be very accurate. So these rates, we cover 1 mile per minute if you're going 60 miles per hour. 60 miles per hour, 80 miles per hour, 100 miles per hour, even when you consider airplanes that would go 300, 400 miles per hour, they can actually do 500 and 600 and 700 miles per hour. Those are all pathetic speeds, including the all of the speeds that we have, because if you are to drive at 60 miles per hour at the path that is the orbit of the Earth around the Sun, what do you think, how long would it take you to drive once around the Sun? To take the same path that the planet takes around the Sun. So you have its elliptical path, so the Sun is in one of the focal points, here's the planet Earth, and it's just going to go around, right? So if you are to drive on this path, how long do you think it would take you? You're driving 60 miles per hour. What is a long time? 7 hours, 24 hours, a week, a year, 10 years. What do you think? Just give any number. A year? Anyone else? I need just one more. And I'll tell you, I promise. 60 miles per hour, the orbit of the Earth. Oh my God, someone say something so we can continue. 2 years. All right, so we have 1 year and 2 years. It will take 1,111 years to drive once at 60 miles per hour. That's how pathetically slow 60 miles per hour is. Right? And then we have a speed limit of 25. That's how long will it take you to go once around at 60 miles per hour. So the planet will catch up with you and crush you 1,111 times. Because the planet does it in a year, and you will take 1,111 years. So, on average, the planet going around the Sun is about 1,111 times faster than 60 miles per hour. This is how sad we are as a species. All right? So now, if I have a path, I will call that path S of t, which we say position function. And since it's in time, it's in respect to time. So I can come up with these functions by observing the motion of the object in time. For instance, here is an experiment, everyone. Look at this now. Don't worry, I'm a professional, even if you won't do it. Observe the path of this object now. What do we see? We're seeing, right? This is the downward opening parabola for what we call parabolic motion. So you can put this in time, and you can say that the object went from, so y of t, which is our s of t, is -1/2 gt squared plus initial velocity times time plus y0. You learn this formula in physics. So now, this is an example because what I see here is -x squared, -t squared. That's a downward opening parabola. The rest are things from physics that we add in to make the formula work. So I have gravity, initial velocity, initial height, because it is important. All of these obviously are important in order for this particular motion to take place this way. Gravity will make sure it falls, hits the ground. Initial velocity and your height, right, are the specifications of you throwing this, which is why we want specific people to play basketball, why we want specific people to play soccer, and so on, right? Because different characteristics, right? You want to have a tall person playing basketball because it's easier to make that hoop, which is higher up in the air. So we have some kind of a path function, and you will have a particle on that path that is going to be launched, and then it's going to end up somewhere and hit the ground. So now, what is that famous stuff that Newton did which made him immortal? Well, Newton said, if you have a position function, s of t, position function, clearly it's s of t because there is an s in the word position, right? We wouldn't want to call it p of t. That would ruin it. If you take the derivative of position function, you are going to end up with ds dt, which we called velocity function. And then if you think about this, you have s is position measured in either meters or feet or whatever, miles, and then you have divided by time, right? So you have miles per hour or meter per second. And then you take another derivative. So if you have derivative of velocity in time, that will be dv dt, you would get acceleration function. So you have the function, then you have the first derivative, you have the second derivative. There is also a third derivative, derivative of acceleration. Now this one you're going to study in physics, and generally there is not mentioned in calculus courses, which is the derivative of acceleration in time, which is called jerk. You experience this. What are the gas and the brake pedals that you have in a car? What do? They accelerates or decelerates. Great. So they are both acceleration. One is in positive direction, the other one is in negative direction. They are both acceleration. So acceleration and deceleration. So it's just plus A minus A. Now, when we are learning these things, you have to understand that these derivatives are rates at which you are changing something. Look, I can take a small sip. You can't even tell that this level changed by me taking a small sip. Here's another one. Can't even tell. So the rate at which the water left the bottle, because I took the small sip, was small rate. I can do my usual stuff. Half cup, right? So the rate measures how fast stuff is changing. You have the path. The path is something that you will take, let's say a path for you to leave the classroom. It's a line on the floor. I can leave the classroom like this. And it's a path, right? It's not very efficient path, but eventually I'll get out, right? Now, notice that if the object moves in time, there is a change in how much of the path you covered in time. So that's what the rate means. How fast do I get to go from one position to another position, location, on that path in time? And we call that velocity. And then I can make that velocity, which is your driving 50 or 60 or 70, I can make that go faster or slower. So when you are at the traffic light, right, and it's red, I hope you're stopped, right? Your acceleration at that point is 0, your velocity is 0, and you are not covering, as a consequence, any distance. You are standing still at the intersection at the red light. What happens first as the green comes up? You push the gas pedal, right? Acceleration makes velocity, velocity makes you cover the distance. Because your velocity, when you are parked, your speed is 0. You need to change that in order for that velocity to get you to cover. You can't cover the distance if you are not moving with some speed. But you don't gain speed unless you have acceleration. This is not a story of chicken and egg, what came first. They actually both came at the same time. But the thing is that your acceleration causes you to change velocity, causes you to change the position, i.e. cover distance. So that's the way we understand motion and why you are actually here and how you're able to be here, right? Now the jerk over here is what you experience every time you press either the gas pedal or the brake too quickly. You see that? Remember, the rate of change is how fast you change something. If your gas pedal is acceleration, You can press it slowly, meaning changing it slowly. Remember the small sip, right? You don't experience jerk. Or you push it really, you floor it. Or you slam on the brakes, right? Every time you experience jerk, right? Because it really jerks you in a car, right? If you push, that's why you have a seatbelt. Because every time you have to brake when someone brake checks you in front of you, right? You will be flying through the windshield. Or acceleration, right? On better cars that are designed for acceleration. Thrill. When you push the gas pedal, it jerks you, it buries you into the seat, right? You feel it. If you go and get a Tesla, for instance, they have the launch control, the mode called ludicrous. You push that button, it is like being fired out of a rocket. You're sitting in a car. I don't know, have you seen those videos on YouTube? Take a look later at one or two of those. Some people really experience near-death experience as someone launches in a Tesla car because they have an insane launch. Right, so you experience this a lot. So what happens? We don't have to worry about jerk. I just wanted to, put it out there that it exists. There's another level after this, whatever. So these are the three that we worry about. So when you have a position function, and that position function can be your sine function to get out of this classroom because the sine function is just fine, right? It just goes as a wave up and down and you will eventually get out. So I have a sine function and then I take the derivative, I have the velocity function. Velocity function describes how fast I'm going at any of these, right? And interesting is as I'm going like this and I'm making this sharp turn for the sine function, then I'm going and I'm making another sharp turn. Every time I'm making that sharp turn, at the tip of that sharp turn, my velocity is actually 0. Which means that I would be accelerating out of every one of those turns, which is the same way you drive, I hope. You brake a little bit before the curve, you get into the curve, and then midway to the curve, you press acceleration. Right? You push on your gas pedal, and then you accelerate out of the curve. I'm not sure if you're paying attention to those things, but most of the people subconsciously drive that way because that's the way the physics works, right? Unless you're weird, and I hope you never are in front of me because I will run you over because I accelerate out of every curve. So we have 1, 2, 3, and then this one, right? So this one is either, right, acceleration, you're changing, you're braking, or, right? So that's that. So now we can come up with any kind of a function as our position function. Say my position function s of t is given as, I don't know, let's do this one. 3 to the negative 2t cosine 5t, for instance. Oh no, we did the a, so we can. Okay, fine. So you take a look at this function. Now, I understand that not all of you are in engineering, but let's for a moment pretend that all of you are mechanical engineers and that you are sitting in one of your 300, 400 level courses now. What is this function for? This function is for a simple pendulum that is attached. Now, this could be also for spring and rubber bands and stuff like that. So you have a pendulum, and what you do is you bring that pendulum out of its equilibrium state. This is equilibrium state 0. You bring it out, and then you let go. The pendulum is going to pass the point to the other side, and then it's going to go back. But see, in time, it's going to swing less and less and less, and eventually it's going to stop. Right? So no matter what you I have this example here. It's a little bit short on the cord, but if I bring it up and I let go, and I wait a little bit, it stops. That's a pendulum, right? So this is the mathematical equation that describes that behavior. If you graph this with your path that it covers on the s-axis, and you have your time, you pick it up and you let it go, and then it starts swinging, and it dies out. It's this e to the negative 2t that kills it eventually, and it's the cosine 5t that makes it go back and forth, back and forth, back and forth. So if you do this in space, far away from all of the, you land between two galaxies, let's say, and there are no planets, stars, or any large objects to impact you. You let the pendulum do this, there will be nothing to stop it, because there is no air resistance, there's no gravity there, so it would just kill this term, and you would just have a cosine, and it would be doing that forever. But here on the planet, or if you are close to whatever else large, it will stop due to gravity, stop due to air resistance, stop due to whatever other factors are there. So now we have a position function, and we want to know the velocity. So velocity would be the derivative of position, which means I have to do the product rule, because I have these two functions that multiply each other. So we copy the first, 3e to the negative 2t, times the derivative of the second, which would be negative 5 sine 5t. If you remember from the last class, derivative of cosine is negative sine, and if you have a number here, the number jumps in front. Plus, copy the second, which is this, times the derivative of the first, which would be negative 6e to the negative 2t. So now you have your velocity will be negative 15e to the negative 2t sine 5t minus 6e to the 2t cosine 5t. And we can factor out negative 3e to the negative 2t, leaving us with 5 sine 5t minus plus 2 cosine 5t. I said 5t, much better. So I have my position function. This would be position. And now I have my velocity function. These are the things that you are programming into your robots, your computer models, right, your software, whatever it is. These are the formulas you're programming in, and then you will be collecting the times and computing the values. So now, for acceleration, you have to take the derivative of the velocity, which is another product rule. But I hope you see that, these things don't look as nice and clean as your homework does, because in mathematics you are supposed to learn the principle and the mechanics, and then when you take the actual courses in finance or physics or engineering, then you will actually use those, right? So let's take a look at an example that has easier calculation. This stuff is a little bit heavy on computational side, but as a concept sits much better than anything else. So let's take a look at this parabolic motion. So you shoot an object in time, and let's say, so s of t position is negative 16.1 t squared plus, let's go with, I don't know, 7t and then plus 2. So when you see 16.1, that means that this equation is in feet and feet and seconds, because your gravity is either given as 9.81 meter per second squared, or is given as 32.2 feet per second squared. Now, the formula that I gave you earlier had a half in front, so half of 32.2 is 16.1. So you are either going to see 4.9, which means your equation is in meters per second, right? Or you're going to see 16.1, which is right, if you are on planet Earth. Clearly, Moon, Mars, and all of the other planets have different gravitation, because one of our biggest issues with Mars is the gravity. Mars is smaller than the Earth. At 2/3 of the gravity, people that are born on Mars and live their life on Mars, if they are to come to Earth to visit for a vacation, let's say, they'll be so weak that if you flick them, you break all their bones. Because the gravity would make them weaker, because there's a less gravitational pull, right? So they would have the weaker structure. Everything would be weaker on them. Less muscle mass, less bone density, less everything. That's the biggest issue. Obviously, poisonous soil, no atmosphere. I mean, everything about Mars is bad. But that's the best we can do now with our primitive technology. So, yeah, we need to support it still, but it's not feasible in the long run. It cannot replace the planet. So now we have this, you're going to have one or the other. So now 16.1 is half of 32.2, so I know my equation is in feet. So now if I want the velocity function, I will take the derivative. That's negative 32.2t plus 7. And if I want the acceleration, I take another derivative, and that's just negative 32.2. Which actually is the acceleration of gravity. When I toss an object, that object is the only acceleration. This has, look at this. Look at this marker. Does it look like it has its own propulsion system on it? Does it have a motor of any kind? Is there a rocket booster on it? Does it have wings and muscles? No, right? So, once I throw this, it will not self-propel in any way. It will just do what gravity says. So, whee, right? And it falls. So, the only thing that impacts it as soon as I let go is the gravity. And we saw it create again this parabolic motion path. What can I calculate from these? Oh, this is, by the way, in feet per second, because it's right, and then you have feet per second squared because it's acceleration. So what can I compute? Well, from the first equation on top, I can compute the object's height at all times. If you ask me, what is the height of the object 1 second into the trip, I just plug 1 for each t, and I tell you the height of the object. If you ask me how fast is the object moving at 1 second, I just plug in 1 second for time, in velocity, and I can tell you how fast. You want to know about half a second? Sure, I'll just plug in 0.5 there. It will tell me the speed of the object, right? The gravity is constant at negative 32.2. Throughout the entire trip, we know that the marker hit the ground. Now, the cool stuff here is to calculate max height. What is the max height? Well, max height occurs here, right? And what is true for that point that we learned earlier in this class? What is true for this point? For the maximum point? Yes?
Velocity equals 0.
Well, velocity equals 0, but sure, yes. That's where we're going. What's true for this point is that the horizontal tangent line has a slope of m equals 0. Now, we know that the slope is the derivative, and the derivative is the velocity, and that's going to be equal to 0. So that's how we get there. So velocity equals 0 is not something that you memorize. You actually know that the horizontal tangency has a slope of 0. The tangent is the derivative. Derivative is velocity. Velocity then must be 0 because the slope was 0. So we can calculate. If I say that the velocity at this time t is 0, then we have negative 32.2 t plus 7. I can calculate at which time the velocity is 0 at the top. Why would the velocity be 0 at the top? Does it look like this marker stopped? Here's another example. You will maybe notice where is the highest point that the marker reaches, right? Somewhere around the projector area. Marker will reach its highest point on this trip. Does it look like it stops? The answer is no. Look, it's a one continuous smooth flight. See, the path that this thing has its horizontal and its vertical component. Horizontal is the constant one. Vertical one is that first it goes up. When it reaches the top, then it goes down, right? Well, can you drive your car forward and in reverse at the same time? No, right? At one point, you actually have to stop and then go the other way. So it's the vertical motion only that stops, but the one that goes across does not stop. So you have a constant velocity forward, the one that is on top and the bottom, that one. Now, you can see that if you toss the object vertically up. This bottle that I'm going to throw up now, maybe I should be able, because it's going to fly all over the place. Let's find, this is going to unwrap. Here. Perfect. So, this mouse is going to fly up now. Notice that when this mouse reaches the highest point, it's going to stop, and then it's going to go down. So, yeah, it goes up, stops, and then changes direction, comes down. So that motion combined with the forward motion gives the illusion of the, not illusion, it is continuous motion forward, but it's the one, only the component that goes up and down is the one that stops, where the component that goes forward never stops. So from here, now, you just subtract 7 and divide the number. That's not something that is now nuclear physics over here. Even if it was nuclear physics, you still sit down and learn it. It's negative 7, negative 32.2 t. So when you divide this, you get time equals 0.22 seconds. So now we have the path function, let's say me throwing a marker, which is actually bad because I'm tossing it from the 2 feet height, so it's gonna be one from the bottom, right? And we took the derivative to get the velocity, took the derivative to get the acceleration function, and now we set velocity equal to 0 to come up with a time at which we have the maximum height. Now you take that time and you plug this time of 0.22 in your position function, and you will be able to compute the maximum height. So that was 7 and then 2. Okay. So plus 7 times 0.22 and then plus 2. So now you run this calculation in your abacus and you will get this. So negative 16.1 in parentheses 0.22 squared plus 7 times 0.22 plus 2. 2.76 feet. So that would be the max height, because the velocity was 0 at this time, 0.22, and when it reached that time, it reached the maximum height, and then after that, right. So you can calculate maximum height and the time at which maximum height occurs. You can calculate time of the trip and all of these other things. I mean, there are a lot of things that you can calculate, but obviously you will expand on this a lot in your physics class. If you take physics class, you should. It's fun. It's cool. We're going to move to another application of this, and that would be the growth models. So you study y equals ae to the kt as the exponential model. And depending on what you want to apply, because this applies in all areas of your existence. If you want to talk about the money, you can say that the amount is equal to principal e to the rt. So this is money. It's called continuous compounding. If you want to talk about biology and population, your P equals P0 e to the kt, and now it's population. To talk about biology, population of tigers or amoeba, I don't care what it is. Then you have that the mass is equal to initial mass e to the kt. This is loss of mass, also known as decay, and you have a whole spiel of things under this umbrella. One would be environment, because you can calculate the decay of garbage, because garbage would have plastic and all of the other things, also organic garbage and inorganic garbage, so everything has half-life, or how fast would it rot and disintegrate in the soil if you bury it. More for environmental would be how fast you get to, how fast would the nuclear waste from nuclear power plants that we use to produce electricity. So that's another environmental concern. We use the half-life and all of these things, we'll see that. So that's all environmental. So garbage, nuclear decay for radioactive waste and so on. But you also are talking about carbon dating. This is not two carbon molecules going out to a date, having dinner and stuff. This is carbon dating is used to figure out how old something that was organic is. So if you dig up a painting or a scroll or a piece of painted like a dish or something, like a vase, it has to have organic materials. You can't go and carbon date the pyramid because that's a stone, right? It has no organic component to it. Anything that came from a plant or a tree or a plant, tree is a plant, or an animal, you can carbon date because it will have carbon C14 in it, and you can see how much is there, and then you can accurately predict how old something is. So you can use all of these formulas. So now we're talking history, we're talking environmental sciences, we're talking about also in the medical field. You use it a lot because you can model the spread of the infectious disease. For computer science majors, you can observe the way the virus, computer virus is spreading, just like human virus is spreading in the population. So this one model covers pretty much all walks of our existence. Electrical engineers, you will use it to charge and discharge capacitor and a battery, and those are obviously very important components in your circuits. We already seen mechanical engineering and so on had something. So it's just everywhere. Exponential stuff is everywhere. Now we're going to take a look at the population, because that's the one that it's cool. And for this population model, which is population at any time t is the initial population times e to the kt, I like to go to this website. I just Google population clock, which doubles as the doomsday clock. And if you go to this website, you see the population changing. And I've been following this website now for 10 years, okay? Because I've been teaching this class. Well, maybe not 10 years, maybe 7 or 8 years. I've been on this website at least 4 or 5 times a year. And I pretty much have all the numbers memorized because I see it and use them so often. You see the population, world population on the side ticking. Last year that was at 7.4, now it's at 7.55, right? 7.42 last time I had this last semester, which was in the fall. And another thing that changed, other than adding another 130 million to the world population since, is the 10th spot. You see Mexico there, right? It used to be Japan. So the 10 most populous countries in the world, none of these changed other than Japan losing its spot to Mexico. So China, India, United States, Indonesia, Pakistan, Brazil, Nigeria, Bangladesh, Russia, and then 10th, Mexico. It used to be Japan there, but Japan is now experiencing, well, it's not now, it's experiencing for years, decline in population, rapid decline in population. There are some predictions that they're going to disappear as a nation in like 100 to 150 years. There'll be no more Japanese. because of what's currently happening there. Germany is on its way to the same thing, and we started chipping on it. This is the second year in a row where the population, the amount of babies is under the replacement level. Replacement level is meaning 2 people make a baby. Well, 2 people should make 2 babies because that's the replacement level. If you have 3 babies, you are above replacement level. If you have less than 2 babies, then you are below replacement level. Now, for 2 years in a row now, America is experiencing below replacement level, which is what Japan started approximately 15 years ago. And they are at that now path to extinction. So we have pretty much the same beginnings. Germany is in that as well. But Germany is at 80 million, so they don't make it into top 10. Japan is the only one that fell off. So now what we can do is we can go and take a look at the population at some point in time, which you can pick. I don't know, 1940, 1950, 1980, whatever you want to pick. We don't want to go too far back because these models are bad. These models are bad, these formulas are bad, because they, well, we'll see what the issue with these models are, but what year should we take as a reference year in the past for population?
1900.
That's too far.
What's the limit?
I said something in after Second World War, so go 50s, 60s, 70s, 80s, 90s. 1950 world population in 1950. World population 1950 was 2.5. That's a perfect one. Wow. 1950, the world population was 2556. I'll just do 2.556 billion. And now we have 2019 with the population clock. It's the same number, except it has a 7 in front. 7.556 billion. That was a really, I wouldn't hunt for that. That's a 5 billion people added in how many years? 69 years, right? So 69, we can round to 70, it's fine. So 70 years. I can switch now. You don't have to watch it. You don't have to look at that stuff. Here is the specs. So in 1950, we have 2.5 billion. And now in 2019, we have 7.5 billion. Now, the carrying capacity of the planet is a number that is projected to be the maximum amount of humans that planet can sustain. We need to eat. We need to have resources, right? Which are gone through mining and so on. There is also gas, right? Because we still explode dead plants and animals to go from point A to point B at 60 miles per hour. So we all have to have a place to live, right? So you want maybe the house and the backyard. That takes space. So carrying capacity of the planet is anywhere, depending on which scientist you talk to, anywhere from 10 to 15 billion. Does anyone see a problem? How close, how fast? That's my question. Please don't think linearly. Don't think linearly, because you would say, oh, but from 1950 to this was 70 years to add 5 billion. If I just wait another 70 years at 5 billion. No. That's not how exponential models work. You are not going to be at 12.5 billion in the next 69, 70 years. Oh yeah. That would be way over. See, when you are thinking about exponential models, you have to understand what it means to have exponential model. We can draw the pictures for that. Take a look at this. Put this to be a can and put a single bacteria on the bottom of this can and say that every minute this bacteria splits in two. That's how bacteria multiply. They don't go out to dinners and then, you know, have a night out and stuff like that. They just split in two and now they're two. So now, if you say that at noon you have one bacteria and at midnight the jar is full. Jar is full at midnight and you're starting at noon. So you before you went to lunch, you put a single bacteria in this jar, you closed it, and you had the camera there that was recording this thing. The jar was full at midnight. So noon, 1 bacteria. At midnight, jar is full. 12 hours. My question to you is, when is this half full? At what time? No. No. At what time exactly is half full? That's it. At 11:59 p.m. it's half full. Because every single bacteria in the bottom half is going to split in two and is going to fill out the second half instantly. Now you say, don't panic. I have another jar. You will be fine. That's us moving to Mars. I have another jar. These are the issues of population that people don't understand. So here's another jar. So the full-blown panic at midnight, don't worry about it. We got another jar. Exactly. When is the second one full? At 12:01. Because every bacteria in the first jar splits in two. That creates just another jar. That's called exponential growth. It's not linear growth. So when you're experiencing a 5 billion population here, difference, it's not the same when you have this many people make babies and when this many people make babies. You understand that? Yeah. There's a big difference. These guys are going to make much more babies than these. Because there's 5 billion more of them. Right? So 5 billion difference. So now that you're understanding the exponential and how fast we get to be, and would it help if I bring in another 2 jars now? No, because at 12:02, those are full, right? The first jar fills the first of the one that I brought, and the second one fills the second one, right? So you can bring 16 jars, and you're still only 4 minutes in, right? It goes from 2 to 4 to 8 to 16 to 32 to 64, right? So yeah, we might have a slight problem. Let's see how doomed are we. So your 1950 now will be casted as t equal to 0 because we don't want to drag these thousands around. And at that level, I'm just going to round these numbers at 2.5 so that I can have my 0, 2.5 as the first point. Now, anytime when you have t equals 0, then immediately the second value is your initial point for exponential models. So we immediately have that p of t is equal to 2.5 e to the kt as exponential model. And now we're going to use the second point, which is 69 and 7.5 as the point. So now you plug in 7.5 here, you have your 2.5 here, and you have e to the, and now this becomes 69k. T is 69, which is the time. We can round to 70, but it's whatever. Divide 7.5 by 2.5, right, to solve, because we need to calculate k. We got 3 equals e to the 69k. You will ln both sides to free up that exponent up there. So your k is going to be ln 3 divided by 69. Keep 4 decimals, 4 non-zero numbers. So we have our ln 3 divided by 69 would be 0.01592. See, these are the 1, 2, 3, 4 decimals, 4 non-zero decimals. So I'm not asking you to keep the 4 decimals, because sometimes you're going to have 5 zeros and then the numbers are going to start. These are called significant figures. The non-zero numbers are called significant figures if you take your chemistry and physics and so on. We need 4 of them for our exponential models. Otherwise, the error that you get is going to be too large and your calculations are going to be garbage. So now I have k, and I can finally put the population model for the current state, which is 2.5 e to the 0.01592 t. This will be called exponential model. So now, which school of thought are we going to take for the carrying capacity of the planet? Meaning, once you reach that, there will be not enough food produced for everyone who lives on the planet. There will be not enough mining. There will be not enough fuel. There will be not enough, right, to distribute between everyone. So should we take 10, 11, 12? It is between 10.2 to 15.2. That's what I've seen in research. So which number should we take?
12.7.
12.7. Great. So let's set carrying capacity at 12.7. So when is the population 12.7 billion? You just want to be safe, I understand. So 12.7 is equal to 2.5 e to the 0.01592 t. Same, right? Divide by 2.5. So we have 12.7 divided by 2.5. That gives us 5.08 equals, leave some space to put the ln in. Ln both sides. That kills e. So we have ln of the answer divided by 0.01592 to give us t equals 102.09, so just 102 years. If you are going, whew, I'll be dead by that time. I don't think I have to worry about that kind of world war. I hope you won't be dead. Not to witness it, but when is this happening? Is this 102 years from now?
102 years from the 1950s.
Yes, it's 102 years because 1950 is our reference point of 0. So it's 1950 50 plus 102. Right? So we have a 2, we have a 5, we have a 0, and so 33 years from now, you'll be alive, right? And that's if the carrying capacity is actually 12.7, right? If the carrying capacity is 10.5, it's going to be much sooner than that, right? Do you see how doomed we are? Yeah, it's time to panic. Yeah. So, what can we do with our calculus? None of this was calculus, by the way. It's all pre-calculus 1 calculations. We haven't done any calculus here, right? So what is the calculus of this? Calculus is when you take the derivative of the population equation to come up with a model that calculates how many people you are adding per year. Adding people per year. Miles per hour, right? How many miles you go in a unit of time, which is hour. How many people do we add in a unit of time, which is a year, right? You don't add people by hour, right? It takes 9 months to cook up a baby, so that's going to be at least a year, right? So we take the derivative dp dt, which is 2.5 times 0.01592 e to the 0.01592 t, and we multiply these two numbers to come up with a rate of population increase. So 2.5 times 0.01592 gives me 0.0398 e to the 0.01592 t. Now, this formula calculates number of people added to world population in any given year. So are you interested in how many people are we going to add this year or next year? Let's do next year. It's easier to do the subtraction. It's 2020. So for 2020, there we go. We have t equals 2020 minus 1950 to give us 70. Plug in t equals 70. So the change in population for that particular year, which is next year, is going to be 0.0398 e to the 0.01592 times 70. Now you get to, punch all of this in calculator in one shot, no lns or anything like that. So we have 0.0398 times e raised to the open parenthesis 0.01592 times, whoops, didn't catch my 5. So 0.01592 times 70. Close parenthesis. 0.1213 billion. So we're going to add about 120 million people to the planet, which sounds right, because as I said last year, when I looked at these numbers, it was 7.422 or 23. So last time I did this. Well, actually, I can go back in the lecture and find the exact number, because I always use the exact number from we have the history of the, right? But it was this, right? It was like something like that. So if the difference is no 7, not 4, holy nightmare, 7. So in 0.4, 7.423. There we go, much better. So that was what I used the last time, and that's about 1.1. So sorry, 0.123. Yeah, it sounds right. The rate at which. So about 120 million people at it. Now, this model takes in account the war, the cancer, the AIDS, natural death, people texting. Yeah, it takes everything in control. Now, it's a bad model, but it's good on a short run, which is why I didn't want to go back to 1800 or 1700 for the population. And I can't really run this model into 3074 because the model is bad. Exponential model that we are using is just a basic exponential function that looks like this. And if you take a limit of that population as time goes to infinity, it is telling us that there will be infinitely many people, which is, we know it's bad, right? So you will later on learn logistics models, which are much better because they take in account the carrying capacity as a limit, because we need to have that. Because the resources are finite, the size of the planet, meaning places where we can live, is finite. We don't live very well in deserts on ice caps. And the water, the 3/4 of the planet is water. The deserts are expanding, the sea levels are rising, right? So the livable land is constantly reducing, right, in area. So we have a smaller surface area to live at and grow food and do all of these things every year. Is smaller and smaller, and population is rising at the rate. So this is what calculus allows us to do this type of scientific research, and you can go and take a look at numbers. You have the equation, you plug everything in, you calculate, and then you know what is the approximate year when we are going to be in a big trouble as a species. Now, obviously, as the numbers change, that year changes and so on. So it fluctuates depending on the situation. So that's the way to use the calculus, let's say, in biology, and whatever else would fall under the, I need to know the population. Maybe you can talk about politics, you can talk about policy, you can talk about, there's a lot of things that you can get out of these numbers that we compute from here. The last part of this lecture that I would like to turn to would be business and business decisions. There are those, there's a statistic out there that says that 99 of businesses that start fail, it's risky business and so on, which is true. And that comes from a simple place that, people in general don't know basic mathematics. So they can't balance stuff, and they start little private businesses, and then they fail because they just suck with money. It's very simple, right? So I would like to take a look at the production and some other stuff. This is really cool because you can see in which way you can use calculus to make business decisions. For instance, you have, let me just find where the statement of the problem is. Okay, let me just define the terms first, and then we'll talk the rest. We have Do you know what the profit is? Or revenue?
Oh, yeah, revenue minus total.
No. What is okay? What is revenue? Yeah, just in words. No equations. I'm not asking for any equations. Just what is revenue?
Total money like received.
Total money received for, for selling a product. For selling a product. Whether it's apples or a service, right? Let's say you own a hotel and you're renting a room. You don't have a product, right? You're renting. So revenue is the total money received, and the cost is what? Expenses. What would go into a cost? Payroll. That's one of the worst ways to reduce the cost of your, right? The most inhuman ways, right? To reduce the cost.
Yeah.
Blizzard Entertainment fired 800 people.
That's the way that most companies do it.
Yeah. 800 people lost their jobs because they wanted to cut their cost in a year when they made record profits.
Those microtransactions.
Yeah. So now, okay, so that's the cost. Also, electricity, cost of, like if you take a look at your MyMathLab and compare it to your textbook. What's textbook cost to buy it? $250. It's Calc 1, 2, and 3, and you get the book. Is the book updating itself? Does the book have any type of pictures that you can manipulate inside? Would the homework tell you whether you are right or wrong on all problems?
The back.
Yeah, in the back, but only on even and only on odd, and not all of them either, right? Compare that to MyMathLab. MyMathLab has the same book uploaded, but it also has all of the other bells and whistles, which includes the homework, which grades itself, gives you all of the steps. Help me solve this, email instructor, and in addition to that, it generates new problems off of the same text. So when you do the problem, mess it up 3 times, it changes it on you. So you have to do everything from scratch, right? And how much is that? It's $100.
Yeah.
You have 5 times better functionality for much cheaper. How's that possible? Well, think of the costs. You have a bunch of programmers that put that stuff up, right? And what is this delivery method? It sits on a server, and if you want it, you swipe a credit card and you have access to it. What's the path that your textbook takes after it was printed? Well, no, before it was printed, right? You had all of the editing and all of the working, right? So that's, and then what happens? Then you have to go and print it. Then you have to create that big cover. Then you have to put them all in boxes. Then you have to ship them on a truck everywhere. You're not talking just United States, right? You ship them everywhere on trucks and airplanes and so on. Then they sit in a warehouse. Well, that's a cost. You have the cost to load and unload and drive and the gas and the insurance for the truck and the new tires for the truck. And then in the... yeah. Do you understand the cost? These companies don't want to make books. They don't want to make books because it's too much of a cost. They want to go online. And MyMathLab is one of those, and a lot of other ones have their own thing as well, right? So we have profit is the money that you keep once you take your revenue and you subtract the cost, which was how much you used, right, to do this. Now, cost analysis is a very interesting thing. If you are able to manage and well control your costs, then the costs would go down to a minimum, which means that your profits would go up. Do you want profits because you want to be greedy? No. You want profits because you want to be competitive on the market. Where would this market be if there was no research development and making a better product? If the first iPhone was still the only iPhone on the market, would they be even relevant? I mean, they're irrelevant anyway, but let's say. Right? Right? So, the thing is that if you have a company, you will have competitors. And when you have competitors, they are going to fight to make the better product. And then you have to fight and make a better product. In order for that, you have to have research and development and engineers, right? And that costs money, right? So your profits are going to be investing into creating a better product, creating a new product, creating a better car, faster car, more efficient car, creating finally electric cars so that we can get away with the other cars, right? That's that. So now, when you're talking about the cost, there is the average cost, which is the cost function divided by the number of units produced. So, cost function divided by units produced, and we call that C bar. So C bar is the cost function divided by. Okay, and then we have marginal cost, which is simply the derivative of the cost function. You can also say dc over dx. Marginal cost is the derivative, and we'll understand what it does when we get to it. The cost, yes, of a single item. And we will understand, when I do the example, we'll understand exactly where it falls. So now, average cost and marginal cost are different things, and clearly average cost is the one that is just your average, let's say, speed, and your marginal cost would be your instantaneous speed, which is what your speedometer shows.
So what would be the derivative of marginal cost?
Nothing. So now what we're going to do, well, it will be the change in marginal cost, but yeah. So now we want to take a look at a small business. And this particular small business will be making 1,000 units of something. So 0 less equal than x less equal than 1,000, small business. And their cost function is given by negative 0.02x squared plus 50x plus 100. Now, when you have cost functions, you have something is called a variable cost and something is called a fixed cost. Variable cost is the cost that goes to your product. So for the raw materials and things like that. So electricity that runs the machine that makes the product, plastic that you make the product out of, salary of your worker that was there to make the product, toilet paper in the bathroom, right? All of the stuff that it's per product, right? And then you have fixed cost. Fixed cost is you purchase the machine. It's a one-time $5 million expense. You set up that machine in a factory, and that machine does the work. Maintenance of that machine goes into the variable cost, right? Because you don't have the maintenance on that machine all of the time, right? It's whenever something breaks, you fix it, right? So fixed cost, you purchased a building, or if you're renting the building, goes in the variable cost, right? So you have your fixed costs, which is you purchase some stuff once, and then you have your variable cost, which is per unit made. So when you create the cost function, now you can analyze all of your costs, and we're going to analyze, they say, for 100 and 900, right, out of 1,000. So first I have to create my average cost function, which would be the cost function divided by x, which is, you just divide by x everywhere, right? So it's a negative 0.02x plus 50 plus 100 over x. So that's our average cost. And now we have a marginal cost, which is the derivative, negative 0.04x plus 50. And I'm going to box these two because I have to refer back to them. So now what do I need? I need the average cost for 100 units made. Let's plug in 100. 0.2 times 100 plus 50 plus 100 divided by 100, and that's going to be negative 2 plus 50 plus 1, which is 49. 49 what? Potatoes? It's dollars per unit. So on average, it costs you $49 to make a unit. I don't care what this is. It could be shoes, could be cars, you know, if it's in thousands. It doesn't matter what it is. It costs you $49 to make one on average. So can you set your price to be 50? You have no profits pretty much, right? So you can't see, this is important, because how do you know what you are supposed to charge for your product? If you charge less than what the cost is to make it, you're going to kick the bucket very quickly, right? Remember, 99% of businesses fail. There's a reason. Now, let's see the cost of the 100th item. What is the cost? Because the upper one is average, right? What is the most expensive item to make? The first one, right? Because if you just make a first item and you never make any items after that, what happens? That item absorbs the cost of the $5 million machine you bought in, you know, you wanted to make 500,000 units. You just made one, right? Does it make sense? So the first item is the most expensive item, and then as you keep going, the cost goes down for every next item. So let's see, it's negative 0.04 times 100 plus 50. That's negative 4 plus 50 equals 46 dollars per unit. So this is what we want to see. If you have the cost analysis, you know it's all good and solid, the numbers come out this way, you go, phew, right? Because you see that your 100th item costs less than the average. That means that the production costs are going down as you are making more units, right? So that's good. Now let's calculate for 900 level. So if I have 900, that's going to be negative 0.02 times 900 plus 50 plus 100 divided by 900. So now this is negative 18 plus 50 plus, and 1 divided by 9 is 0.1111 goes forever. So 18, that's 32, right? So 32.11 cents dollars per unit. Perfect. I love it. I love it because this means that if I'm making more than what I used to make, the cost of making them goes down. My business is going to work in this case. 900 unit is going to be negative 36 plus 50 is $14 per unit. Whoa, nice. So it only costs me 14 bucks to make 900 units. The average is still 32 to make all 900, right? So you can't look at the $14 to set up your price, right? If you take a look at the $14 and you set your price to be $30 to set the one, you say, that's more than double. No, your cost was 32 on average, right? Because there are units that you produced at 100 that were $46 per unit, right? You are using the derivative to see what is the cost of that particular unit away from, from the average. And you want that number to be smaller than the average number at all times. So now we have this calculation, and this is what the healthy stuff should look like, because we see that the more units we are making, the cost is going down, and the cost of each individual unit down the line significantly goes down as we keep moving. And that's it. I hope you're not disappointed. Bye.